In this screencast, I'm going to look at solving this differential equation, and it's a linear differential equation, and so I'm going to be using the integrating factor method. So that you can see it's linear, let me just write down what the general form of a linear differential equation is, and you might have to rearrange your equation to get it in this form, but ours is already in the right form. dy by dx plus g of x times y equals h of x. That's the standard form for a linear differential equation. And hopefully you can see that what I have multiplying the y, which is g of x in my notation, in this case is minus 2 over x. The negative sign has to be included in the g of x because of the plus sign in that form there. And also on the right hand side here I've got h of x, which is 2/3 of x to the 4. So I've got my equation in the right form, and in order to use this method, the first thing I have to do is find the integrating factor. And we denote that usually by p of x, and it's given by e to the integral of g of x dx. So what I have here is e to the integral of minus 2 over x dx. And I need to do this integral and then simplify as far as possible so that the next step will be easier when I come to do it. So what I'm going to do is take out the minus 2 as a constant multiple, and if I integrate 1 over x, I get log of x. So then, using log rules, what I have is the minus 2 comes up as a power, and in fact the integrating factor is x to the minus 2. So what I can now do is rewrite the original differential equation, and again I'll put the standard form up first. The standard form is d by dx of y times p of x equals h of x times p of x. What's actually happened here is the original differential equation has been multiplied through by the integrating factor, by p of x, and then the left-hand side has been rewritten as the derivative of a product. And it's this rewriting that enables us to solve the differential equation quite easily. So in this particular case, what I have is d by dx of y times x to the minus 2 equals h of x, which has disappeared, but it was 2/3 of x to the 4. So I've got 2/3 of x to the 4 times by p of x, which is x to the minus 2. So the differential equation is now in the form d by dx of y times x to the minus 2 equals 2/3 of x squared. And I'm not going to bother to do this, but what you ought to do at this stage is check that this is indeed correct by differentiating out this left-hand side. What we've got here is the derivative of a product, and if you use the product rule, you can differentiate it out. If you then simplify the whole thing, you should hopefully end up back where we started with this original differential equation. And that's a good check that things are okay. So I'll leave you to do that. Let me now just finish this. We now have something which can be integrated directly, because on the right hand side I've just got a function of x, and on the left hand side I've got d by dx of something. So if I integrate directly, I get the left hand side is y times x to the minus 2, and on the right hand side I've got 2/3, and then the x squared integrates to x cubed over 3. And I now add the c, and it's important. The c is the constant of integration, and it's important to add it at this stage, at the stage immediately after doing the integral. And then I multiply through by x squared everywhere to make y the subject. So I have 2/9 x cubed times x squared is x to the 5, and the c times x squared becomes c x squared. And that there is the general solution to the original differential equation. And you can check that's right. Again, I'm not going to bother doing it, but if you differentiate this and substitute it into the original equation, you should see that it satisfies it.